Okay, folks, I just want to give you a brief explanation for the exam. So let's go ahead and open the exam from ephraimchemistry.webs.edu. Sorry, it's gonna be Ephraim Chemistry. Scratch that. ephraimchemistry.webs.com. Under favorites, we go to LACD College, and then you find faculty and staff, Ephraim ASPA webpage, and then the exam will be under document staff. That will be the sample exam. And let's open the sample exam 3. That will be very similar to the upcoming exam that is coming up this Monday. So I just want to give you a brief overview for the exam. So once you open the exam, the first question you are going to see is to define ionization energy. Pauli exclusion principle. Pauli exclusion principle simply says no two electrons can have all the four quantum numbers the same. That means you have n, which is the principal quantum number, L, which is the sublabel for you, and then m sub L, which is the number of orbitals or the orientation you can assume, and then you have the spin quantum number. None of these all these four numbers cannot be the same for two electrons. They have to be unique from one another. Okay, that's it. That is the first question. The part E asks you to define the orbitals. Orbitals are pretty much the region around the nucleus where the probability of finding an electron is the highest. I don't need to say that again. Okay, so let's move on. Limiting reactant problem. Should be familiar. Number 3 will be there, which asks you the possible combination of quantum numbers. So note that the first quantum number we have is n, which is the principal quantum number, which is directly proportional to the energy. So the higher the n, the higher the energy. So n can go from 1 to infinity. And then the n is also called level, by the way, which stands for energy level. And then the next one you have is L, which is the sublevel, and it tells you the shape around the nucleus. So S, for example, is a sphere, and P has 3 orbitals which come in low form. 1 low, T, X, Y, and then you got the idea. That is the P. So those are sublevels. And then the sublevels can go from 0 to n minus 1. For example, if n is 1, L can only be 0 and 1. It cannot go any further. So if you look at your choices, the first thing you should look at is the n, which is the principal quantum number. And then you move on to L. So L must be 1 less than the principal quantum number. If you are given the principal quantum number of 3, L can only be 0, 1 and 2. So if the choice says n equals 3, L equals 3, that combination of quantum numbers is simply not possible. And then you move on to m sub L. So that is the number of orbitals. So L equals 0 is S, so you have only 0. And then m sub L ranges from minus L to positive L. So that means you go from negative L to 0 to positive L. That's why if you have L equals 0, you only have one orbital, which is 0. And then L equals 1, you have minus 1, 0, positive 1. And then you have minus 2. If you have L equals 1. L equals 1, I already described. And then I have L equals 2. So L equals 2 will be minus 2, minus 1, 0, 1, 2. So you have 5 possible orbitals, so that makes it a d orbital. And then L equals 3 will be F, because you have minus 3, minus 2, minus 1, 0, 1, 2 and 3. So number 3 is very critical to understand because it asks us the combination. So the answer for number 3, for example, would be if you look at number A, it tells you n is 4, L is 3, M sub L is -2, possible. Look at B, it tells you 3, 0, 1, it's not possible, so that would be your answer. How many orbitals are contained in the following sublabels? You know that already from my previous discussion. Number 5 should be very familiar as well. Electron configuration of a chromium is slightly different because of the stability of completely full orbitals or half-filled orbitals. Let's say, for example, F is completely full when it has 14 electrons. It is as stable when it has 7 electrons. Almost as stable. D can hold a maximum of 10 electrons, so it is as stable when it holds 5. So half-filled or completely full orbitals have added stability. So that is pretty much the story behind quantum numbers. And then you have the 50 points of drawing Lewis structures. So this is structural formula. Remember, there are 3 kinds of formula we described. You have empirical formula that tells you simply the ratio between 2 atoms present, or the number of atoms present in your molecule, your compound. Glucose has 6 carbons, 12 hydrogens, and 6. That means C6H12O6. The empirical formula of this guy will be CH2O. The molecular formula tells you the actual number of atoms present within the compound itself. That's 6 carbons, 12 hydrogens, and 6 oxygens. And then when we get to structural formula, that is where all the connectivities begin. So Lewis diagram is the first attempt of determining the shape of a molecule. So we do know that molecules are 3-dimensional and they interact with other molecules based on their 3 dimensions. So if you get these structures, then biological activity, most of the biological activity of molecules comes from interactions between molecules. That means the shape must be perfectly appropriate for this interaction. For example, when you talk hydrogen bonding, for hydrogen bonding to happen between 2 molecules, you gotta have that hydrogen sticking out with this partial positive charge, and if oxygen is in close proximity, it can form hydrogen bonding. If that oxygen, because of the shape of the molecule, is slightly twisted like this, then there is no really chance for hydrogen bonding. So structure is very important because sometimes it dictates molecule-molecule interaction, which boils down to even sometimes chemical reactions. So chemical reactions simply might not happen sometimes because of the arrangement of a molecule. So if the molecule is pointing down, if the atom is pointing down, for example, another molecule can attack it from behind. So if this is blocked because of the arrangement of other molecules, that reaction simply does not happen. That is what makes structural formula and the connectivity of the molecules and molecular shape completely fascinating. This will conclude my discussion, and this is my trial for the video. Thank you.